HDMI adapter because that's what we have. You don't even need the laptop, so yeah. Actually, close your eyes, everybody. Close your eyes, like this. Do you think you have a talk? If you do, then just raise your hand. I can see when you're not closing your eyes, so everybody close their eyes. They're not paying attention. If you think you have it, close your eyes, up. Raise your hand if you have potentially a talk. Nobody else needs to know, just me. Okay, you're pretty shy. We'll find a solution. If nobody shows up, that will be me again. So we don't want to go there. Please find a talk at about 4:30. So we start about now as soon as everybody's sitting. There were spots over there.
Oh. If everyone has their computers, pull them out because there are exercises you can follow along with. And then I'll be pausing in between to see if anyone has questions along the way. So take a moment. If you can go to the FOSDEM page for this presentation, go to the presentation link at the bottom, and you can get to all the examples from the slides.
Now is the moment to make noise with your laptop. Take your laptop out now. You don't learn if you just listen, plus it's not fun, so. It's mandatory. If you have a laptop, take it out. They're going to hate me, not you. So.
That's fair. Hello. That's fine. Don't worry about it. Go.
So JavaScript is not fun if you do it alone, so you need to help others to get it. For this.
All right. This talk is a little less technical, and it's actually about how do we make the technical approachable. So I would like to show you some ways that we can use JavaScript as maybe possibly the best language for effective learning. So how not only then can you teach with JavaScript, but how do you teach programming at all? What are the best practices for that? And how can JavaScript fit very well with those best practices? How does JavaScript fit very well with open education? And we're going to look at open education as a slightly different thing from open source and see that JavaScript is really the best option for fully open computing education. And finally, we're going to look at what is computing literacy, how can we teach it, and how does the single pane nature of the JavaScript browser, where you can inspect, have the UI and all of the sort of back-end, front-end together at the same time, make it the best language for computing literacy. So each one, there's a little link of exercises within each slide. I'll talk over them. I'll give you guys a minute or two to look at them, and then questions. So we'll be pausing 3 times for questions and answers. First, we're going to think instructional design. How do you teach programming? I think the first sort of not necessarily intuitive thing is that you need to explicitly teach the implicit. The general knowledge you hear is to get people to think like a programmer. Tell people what you're thinking. Get the students to think along the same processes as you. That is, of course, the end goal. But between the beginning and that phase, there's a lot of implicit knowledge that you as a programmer already have. When there's an error, why do you look at the line that you looked at? Why did you move your mouse to the file you moved it to? Why did you scroll where you did? All of these little tiny things that you don't even think about are actually what a student needs to learn before they can get to the interesting, the strategy stuff that you would like to teach. So find ways to teach people what you're doing, not what you're thinking. The second is to emphasize the process over the product. So this is along the same lines, but now we're going to think, how do you explicitly structure a series of exercises to emphasize the process over the product? It's one thing to just say, all right, build me a recursive merge sort, and while you're at it, think about what you're doing. The focus of that exercise is still the finished working code. The tests pass or they don't, and it's really up to the student's personal discipline and experience whether or not they can document and keep track of what they learned along the way. So the type of solution for this would be to assign steps instead of a final product. Say, I don't care if your code works, but I want your best attempt at these 8 steps along the way to a recursive solution. Context is content. This one is something that's often overlooked. Usually with things like FreeCodeCamp or Khan Academy, the thought is let's simplify the programming environment so students can focus on code. But that is absolutely unhelpful, I believe, in the long run. because coding does not happen in a protective environment. Coding happens in a real environment. It happens with real browsers, it happens with real errors, it happens with other people's code. So context is content. Wherever you place an exercise, the student is explicitly learning what you told them to and implicitly learning how to navigate that environment. If they're spending 6 months on Free Code Camp, that's 6 months that they not only didn't learn how to use the browser, but didn't learn how to integrate JavaScript into their use of the browser. So when you're designing exercises or projects, think very carefully about what's the level of my student, where would they be using the skills I'm trying to teach them, and how do I embed the skills I want in a simple example in context. Which brings to the last point, full complexity, max simplicity. When you're designing an exercise, you're helping someone, you're coming up with a little snippet, think, what is the entire complete task that the student will have to deal with, and how do I reduce that to its absolute most simplest form? So I have an example for this we'll go over together quickly, and it is an example that helps teach this and binding. So what I have here is an example of an embedded resource. That's what I call it. I don't know what they're actually called. The idea here is that the context is the content. Not only did I write a series of explanations on how this works and how binding works and how events work, my example is written in code and it runs. And the student is going to be interacting with that the same way. Ooh, this is weird in presentation mode. There. The student is going to be interacting with this in the same way that they would generally interact with real code. So let's say that you're interested in what happens when we use a free variable by context. So we have a callback function for an event. Inside that callback function is a free variable using this. I want to set that by doing bind. So we can use this little helper function, load. That's 2. Ooh. By binding.
So while it's
there.
being set up, if you could, when you're on that side, come closer so that others can see.
So the student has now loaded just the lesson they wanted, but that lesson is actually written in code, but it also has a helpful log that explains in English what happened as the code executed. So the student can study the code itself. They can additionally study how did it log itself. So it can see not only what happened, what was the source code, but how did the code write its own description, what was the outcome on the screen, and what is happening inside of all of this. Every time they click the button, it's clicking bound DOM element, but we can see that the button they're actually clicking is host DOM element. So when I click it, it prints the information from my bound function, so the bound callback, on the host element if you want to see how exactly that was implemented. You're not reading a markdown, looking at code back and forth, trying to string it together. You are in context, seeing the simplest possible example that will teach this concept. The first step here is even to make it simpler and demonstrate the exact same mechanism taking place with a simple plain JavaScript object. So that is the first bit. How can we make good exercises for teaching programming, and how is JavaScript very useful for that? We had to explicitly teach the implicit. It's not only about teaching the thought process, it's about teaching the implicit skills that allow you to focus on the thought process and not every single bug. Focus on the process over the product. You have exercises, you have words, you have projects, where the explicit goals are to complete a series of steps rather than produce working code. You have context as content. Carefully pairing exercises and projects with a specific learning environment so that where they are studying the code becomes part of the learning objective. And finally, put all that together and you have full complexity, max simplicity. Teach the full complex task in the simplest possible way. Questions? Now I can just go on. We can look at a couple more examples of each step if you like. Yes? So explicitly teaching the implicit. For that, I have an example of what I call expanding. One of the most important skills that we experienced programmers have is the ability to step through code in our head, know which line is going to be executed, where did each variable get its value, how is that changing over time. That is extremely difficult to teach, especially because it's not usually explicitly taught. People just say, read the code and figure out what's happening, and then people don't. And what JavaScript has that's so special is the flexibility of how many ways you can write the same code. So this expanding is a form of refactoring that follows very strict rules. So students don't have to focus on how they're going to do it. They know exactly what's the next step in the process. The first thing, you expand any control flow statements. So you're going to remove the conditions from directly within the ifs so that you can later assert them. There's an example of a while loop below. It's a very similar process. Then you're going to expand the expressions. Using block scope, you split a one-line expression into a series of proper order of operation, single operation on one line. So your code is becoming a lot longer and possibly more difficult to reason with until you get used to it. Then you see that this is actually an incredibly powerful tool because you can start to build exercises, and even you are not building the exercises. The student themselves can build their own feedback mechanisms just by simply putting on the same line a little log.push. So now what a student has is a step-by-step process of what happened as this code executed. Because it's all JavaScript in the browser, they can just simply copy-paste it from the markdown into the console. They fill in some values, and they expect it to be false. Oh yeah. Where was that? This was an error I forgot to fix in the pushed version. Val1. Let's go to the while loop. It works. So for the looping, it's a very similar process. You start with a loop, a for loop, but for loops can always be expanded into a while loop. You put it inside of a block to preserve the integrity of the let, or the block scope variable in your for loop, block the whole while, check the condition, set the initial value, check the condition at every loop, update according to the same rule, expand all the expressions, and finally log it. We'll just set some expected values. So we failed. We did not have the correct prediction. So here you are emphasizing what is the behavior of the code versus the implementation. What did you expect the code to return? And how exactly did it get there? So now what a student has, Firefox isn't always the best for this. They can step through the code. What value did every line of code have at every step? And this allows you to make very good sense of what is otherwise rather opaque code. So that is making the implicit explicit. An example of teaching process over product, I have recursion here. So rather than saying recursion works like this, draw some diagrams, expect them to write working code, say no, recursion is built up of these steps. These pieces. Every recursive solution has the same pieces. And when you're planning a recursive solution, build the pieces in this order, and you can later assemble them back together to a solid solution. This gives students something that they can work on, small, manageable, understandable pieces. So I've given an open-end test, an open-end challenge. But then the steps. First, test cases. Without even running the code, how do you expect that it will behave? You could also provide those as part of the exercise. Base case. Write a function that determines if the argument is a base case, focusing on one piece only. What do I do if it is a base case? What do I do to the operation, to the argument, so I can build back up? The breakdown. If it's not a base case, how do I move the argument closer to a base case? Write a function that does that. You'll notice at each point there are tests along. I'll get to the helper function at the bottom. Build up. I have two recursed partial solutions. What do I do to get them closer to a full solution? Finally, simply call them in a scaffolded recursive solution. If it's a base case, turn around. If not, we're going to break it down. We will recurse, and we'll build back up and return. Students can now then factor out their functions, just copy-pasting the body of their functions where the function call was. They can collapse it if they like, and convert it into a formal recursive definition. And the step from here to here is actually relatively simple. So what you have also is not only a good way to teach students the process of solving a problem, but you're making a manageable step from the practice to the theory. And the mathematical theory is often very difficult to get students interested in and to even understand. If you want a nice little challenge step, you can see how to compose those solutions. So I'm actually taking longer than I thought. Context is context. Look at these on yourself. I took a simple exercise from Free Code Camp and just set it up in a whole bunch of different learning environments. Open source does not equal open education. Open source is open access to source code. Open education is open access to education. Open source educational resources is anything built for education that has an open source license. But that doesn't mean that it's easily adaptable by the people who will be using it to learn. So for a simple example, I made, here's a JS Parsons. It builds Parsons problems for students, and it's actually the teacher that has to build it. There's full documentation on how to use it, and it's not immediately obvious how a student would be able to build their own Parsons problem. So this is an open source educational resource that I would claim is not fully open education. However, with a little bit of reworking, you can end up with the Parsonizer, where a student simply types in whatever. They can copy-paste the code from whatever exercises they're looking on, and all of a sudden they build their own Parsons project. So the difference now between open education and open source is how readily can the students and teachers who are actually learning adapt their content for themselves. So open source is not open education. We had an example there, the Parsons library versus the copy-paste Parsonizer. So what is an example of something that's open source but not open education? I would say Free Code Camp. Yes, the source code is open. Anyone can, in principle, rebuild their own Free Code Camp and run it. But practically speaking, it's not only completely out of range for any student, but most teachers probably don't even have the technical knowledge or the time to fit and adjust Free Code Camp to match their own needs. So it is open source, great open source educational resource. It is great free education, but it's not open education. Not open source, but open education is Replit. Replit does not open source its code, but the tools that they have for teachers, classroom management, exercise creation, running code in a zero install environment is outstanding. So Replit is an example of closed source, open education resource. The perhaps best one, I believe, that is both open source and open education is a tool called Python Tutor that you can also use to study JavaScript that teaches the notional machine. I'll talk about that in the next step. So what is a quick example of something that is both open source, open education, and realistically accessible to a student? It is this. A student can inspect. They want to study coercion because that's difficult. So what happens if we take a string, -4, a number, 4, we add them. I expect the result of this operation to be Boolean true. I got it right. What if I said false? I would get it wrong. And what if that's not a Boolean? It would tell me. So I'm constantly getting feedback in the console. Students are learning how to read the dev console, look at the code. They're learning how to, in their heads, break down long expressions to debug them. And furthermore, the source code itself is very accessible to a student. There's a simple function that casts to types. There's a simple clear func table, and a slightly more complicated handler function that's long but has nothing extremely difficult in it. And this over here is simply an HTML table. So this is an example of a very powerful open educational resource tool that is also realistically open source to students. You can imagine a student after a couple months getting the confidence to build their own tables for expressions that are troubling them, or to make their own little courses and remix and share between themselves. So open source is not strictly equal to open education. Finally, computing literacy. What is this? How do we teach it? So I'm going to skip defining exactly what it is. I'll do that in a second by showing not a sentence, but a project that a computationally literate student should be able to build realistically after maybe a year of study. First step, though, is honesty. This is intellectual honesty. If you want to truly teach computational literacy, you need to teach students that what is actually happening. Do not put it in any other words. Do not use analogies. Teach what is and expect that students can learn it. So this goes to Python tutor, teaching programming first from a notional machine, not using analogies, not using custom environments. Let's teach students in place using clever methods. Agency. Students should learn that they have agency over the digital tools that they use. Of course, you're not going to have it over everything, but they should learn that it is possible. And so that's why in the previous slide, I was advocating for open source resources that are also open education. Students can modify them themselves, adapt their own courses. Ownership. So this is now beyond the student to the whole community, the schools, the teachers. They should all be able to easily adapt whatever content, whatever courses to their own needs. So this is again where Free Code Camp isn't ideally open education. It is a very good course, but it's very long and it's very prescribed. It'd be difficult to adjust that to different lengths, to slightly different needs, different levels. Integration. Students can't just learn programming. They need to learn how the user, how the computer itself, how the source code, how the developer, how there's an entire sort of space, a communication space built around a running application that has real-world impacts. JavaScript is exceptionally good at teaching this through what I'll show you in the final project, the ability to have a working application in the DOM, the dev inspector tools, source code, printouts, all simply live on an open source hosting like this github.io. Finally, preparation. The goal of computational literacy isn't to create professional ready students. It's to create students who are prepared to go on and learn whichever path they'll later need, whether that is to be a developer, whether it's to simply be an artist, anything. But to be living in the world with a basic understanding of what is computational literacy and how does it work. Why is that relevant, and that they do have some say. Here is an example of a final project that I believe a student could be able to build after 1 year. It contains dynamic documentation, automated testing and feedback through a simple run tests function that can easily be understood by them. This is the only source code that they also didn't write for the whole project. It just reads, it just takes in a function, arguments, passes them through, compares them, and logs. A student can see which ones failed, which test cases failed. What are all the functions available? Let's see. I want to cheat. We can now check our log, and we can see that someone cheated. Cheating. Input 1, scheduled, blah, blah, blah. What is also super, super important as far as computational literacy goes is the idea of applied computing. And how do you embed a problem from the real world into the computational space? And here we see that with embedding and debedding. If we look at the model, we can see this here, the challenges. We can look at the way students have organized their database. They have two functions, embed and debed, that map from strings to array of char codes. They perform all of their sorting and all of their removing extra elements on the array of numbers and map it back to a string when the user wants to see what's stored in memory. So it's super simple. It's things that can easily be done, right, within the first couple months. But it's the fact that you're having people do this instead of something else that sets them up. None of these concepts are impossible to understand, but they need to be simplified and explicitly taught. Questions? Or is there time?
One question.
There's one over there.
Thank you. Are you using a debugger in one of your teaching examples? Because
Everything.
I've everything.
It's always the built-in debugger. And so that's one of the whole things, is you have zero install openly available tools. So all of the exercises are built in just the Chrome or Firefox.
Okay,
sector.
sorry, then I meant specifically pausing on a specific
Ah.
line and